Welcome to the Module 4. We will learn data exploration of descriptive statistic in this module. Descriptive statistic is a statistical model used to summarize, organize, and categorize the fundamental features of a dataset. Its purpose is to describe the main characteristic of data through numerical values, charts, and graphs. In this chapter, we will learn some concepts and Excel functions related to the descriptive statistic applied in the business analytics. In any data mining project, one of the very first thing we do after initial data collection is data exploration. This means taking a close look at the data, using simple queries, visualizations, and summaries to spot patterns, check for unusual values, and form some first ideas about what is going on. Data exploration can involve things like looking at the distribution of the key variables, checking relationships between different attributes, running simple summaries, or comparing different groups within the data. The goal here isn't to build a complex model yet. It is to understand the data so we can decide what to do next. So one of the best tools for this is descriptive statistic. It's quick, it's low cost, and it gives you clear numerical summary of your dataset. So in this lesson, we will focus on how to use descriptive statistic to get meaningful insights right at the start of the project. The descriptive analytics is to collecting and analyzing data to better understand variations, which is the differences we see in a variable across multiple observations and how those differences affect a business context. We all know what data is, which are the facts and the figures collected, analyzed, and summarized for presentation and interpretation. Here we have two new concepts: variables and observations. In business analytical concept, a variable is a characteristic or quantity of interest that can take on different values. An observation is a set of the values corresponding to a set of the variables. In last module of database, we talked about column or attribute that stores the values of that variable for all records in a table. For example, in the customer database, age might be a variable stored as a column, and each row contains the customer's specific age. And in context of business analytics, they are identified as variables. So variables can be divided into two types. Decision variables. These are directly controlled by the decision maker. Something like the price of the product, how much inventory to keep, or how much to spend on advertising. Because these variables are under your control, you can change them to influence the outcomes. Another type is random variables. These change due to uncertainty or factors you cannot control. For example, the customers demand, weather conditions, or market interest rates. Since you cannot predict them with complete certainty, you have to plan for their variability and possible impact. So by understanding both decision variables and random variables, descriptive analytics help organizations to see what you can control and what you cannot control, and how both affect their business. So this is the first step towards more robust analysis and better informed strategies. Now let's talk about the data, the facts and the figures we collect, analyze, and summarize for decision making. Data can be organized in different ways. So one important classification in statistics is the difference between a population and a sample. The population is the entire group we are interested in. For example, all customers of a company, every product made, or all sales in a year. Analyzing the whole population is called a census, but this is often costly or impractical. A sample is a smaller subset of the population selected for analysis. For example, serving 1,000 customers out of the million could be a sample. Sampling saves time and resources but must be representative to give accurate insights. To ensure a sample truly reflects the population, we usually use random sampling, where every member has an equal chance to be chosen. And this reduces bias and makes our conclusion more reliable. Understanding the difference between population and sample helps us analyze data correctly and make better business decisions. Another classification method is based on the nature of the data, which can be classified as quantitative data and categorical or qualitative data. Let's start with the quantitative data, also called numerical data. This type of the data answers questions like how much, how often, or how many. It mirrors quantities or amounts such as the height, weight, or length. And next we have qualitative data or categorical data. This type describes qualities or characteristics that fit into category rather than numbers. For example, we can have marital status, like the married or single, and brand name of products, debt default status, types of the medical diagnosis, and extra. So sometimes qualitative data might look numeric, like birthdays or postal codes, but they don't have mathematical meaning. And then qualitative data can further split into nominal data and ordinal data. So nominal data are the labels without any order or ranking, like the letters, symbols, or the gender. They are analyzed by grouping and counting the frequency. And ordinal data have a meaningful order, like ranking grades, grade A, grade B, or grade C. But the difference between the category isn't always equal. Quantitative data can be divided into two categories: discrete data, which are separated, distinct values you can count. So they have a finite number of the values and usually come in whole numbers. For example, the number of the students in a classroom. And then we also have another type of the quantitative data, which is called continuous data, which can take any value within a range of measurements with precisions. For example, the temperature. At last, data can also be classified based on when it is collected. Cross-sectional data is the data collected at the same or nearly the same point in time. It provides a snapshot of a population or sample. It can be used to compare differences across groups at a specific moment. For example, here is the stock marketing table showing the share price and trending values, the trending volumes for different companies captured at the same moment. You can compare prices, trending activities, and industry all at once. On the other hand, time series data is the data collected over a period of time, like the minutes, days, month, or year. It shows changes or trends over time, but of one specific variable. For example, here is a graph tracking the Dow Jones Industry Index from 2006 and 2019. This shows how a single variable changes across multiple time points, helping to identify the trends and the patterns of, for example, this industry index change. So by understanding these two types, business can choose the right analyze to answer different questions. So whether comparing groups at one moment or tracking changes over time. In business analytics, most of the time we're working with the sample data, not the whole population. But before we start crunching numbers, we need to ask two important questions. First is Is the data cross-sectional, meaning it's a snapshot in a specific time, or time series, meaning it is collected over a period of time? And then the second question is each variable quantitative or categorical? So we will leave the cross-sectional data and time series data later. Now let's focus on the quantitative and the categorical data. So these types of the data determine which descriptive statistic we can use. For categorical data, we focused on distribution. That's the frequency or related frequency showing how often each category appears. We also focus on the location, usually the mode, which is simply the most common categories. And then for the quantitative data, we have more tools. Like we'll look at the distribution by using histograms or numeric summaries to see how the values are spread out. We also need to check the location by measuring the mean, median, and mode to find the center. We also can check variability, something like the range, variance, and the standard deviation to see how spread out the numbers are. So now let's check about this one by one. Let's talk about frequency distributions. They're basically a way to take a big pile of raw data and make it easy to understand. Instead of looking at every single data point, we group them and count how often each value or category shows up. So this can be done in a table or a chart. And trust me, it makes spotting patterns a whole lot easier. So say we served 50 people on their favorite soft drink. The raw list may look messy. Coca-Cola here, Pepsi there, Diet Coke somewhere else. So when we put this into a frequency distribution table, suddenly it's clear. Coca-Cola got the most votes. The Pepsi came in second and Dr. Pepper barely made the list. The total still adds up to 50, but now we can see the story behind the numbers. And in business analytics, this isn't just about pretty tables. It's about actionable insights. So if Coca-Cola is your top seller, you might focus marketing there. And if Pepsi is close behind, you make sure that the shelves stay stocked. And if Dr. Pepper is struggling, maybe you run a promotion or rethink its shelf space altogether. So this is the power of the frequency distribution, turning raw data into smart decision. Now let's see how to do the frequency in SQL. So first of all, you need to download the Module 4 Practice SQL file from the canvas. So right here, a lot of students, they made a mistake that they opened the downloaded file straight from the folder. Don't do that, because if you do that, you will open the file without opening your MySQL local database. So we want to open our local database at first, by clicking this local instance, and then going to the MySQL local database and then open the file. Okay, so like what I've done here. And change the database name to your database name. Some of you might have the same database as me using the Lead Business. Some of you might using the database as your name, using your name as database after you've done the first assignment. So it doesn't matter. Just to make sure that your database, you're using the same database here with the database in the left schema list. So make sure like this part, they are matched. You need to run a query and refresh your database, and now you should see 2 new tables in your database. So here, you don't need to highlight any query and execute it because we're running the whole file named the Module 4 Practice. So you don't need to highlight anything. You just need to click the execute and run the whole queries. Okay, and then you can click the fresh button and you will see there were two tables showing here. One of them called audit record and another one called soft drink sales. So let's use the soft drink sales table at first. And we're gonna open a new SQL query file to write a new query, and let's write this query together with me. So the first of all, since we're trying to get a frequency of the drinks from the 50 people, right? So, but like before we do that, the first thing I want to know is how the data looks like. Because if we want to write the query, we want to know what the data looks like at first. So I'm gonna using select all from. So remember what that means? That means we're gonna check all the data from a specific table. So I'm gonna run select asteroid from a soft drink sales table. So by doing this, I can see all the tables. I can see all the data in this table, how it looks like, and then I'm gonna decide what query I will write. So now you can see this is what soft drink sales table looks like. There are 4 columns, including ID, drink name, quantity, and transaction date. So since we're looking at the frequency of the drink name, we don't need other columns. So we only need the drink name, this specific column. So instead of select all, the select asteroid from the soft drinks, we can change it to select drink name from the soft drink sales. And since we want to know the frequency of the drink name, so we can use this query, which is called count asteroid. So count asteroid, which is also the count all, as the frequency. So in this query, the select the drink name means we select the column drink name from the soft drink sales table, and it groups the result based on the unique values in the drink name column. And count asteroid as frequency means counts the total number of the row for each unique drink name in the soft drink sale table. The result is analyzed as frequency, which shows how many times each type of the drink appears in the table. Now let's run this query, and oops, you can see that there is an arrow. So we need to check this arrow. So what it will do is you will right click this arrow and then click copy response and then paste it into here. And we can read this arrow to see what is going on, okay? And this arrow said, in aggregated query without group by, blah, 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 blah. So that means it is pretty obvious that there is a group by statement which is missed. So what exactly is a group by statement? So the group by statement in MySQL groups rows that have the same value into summary rows, like find the number of the customers in each country. So the group by statement is often used with aggregate functions like count, max, mean, sum, or average to group the result set by one or more columns. So you can check more information in W3 School. I provide you the link in the reading material. Now we will remove this error code and add the group by at the end of this query. Please remember we have to add this group by before the semicolon. Okay, because this is still inside this query section. So we add group by drink name, and then we will run this query again. Alright, it works well, and you can see the result showing the drink name and the frequency. Relative frequency is proportion of occurrence of a category related to the total number of observations. It is calculated by dividing the frequency of each category by the total number of the observation. So for example, the relative frequency of Coca-Cola is 19 by 50, which is 0.38. The percent frequency distribution is just another representation of relative frequency distribution. It just summarizes the percent frequency of the data for each being. So we just need to use the relative frequency by 100 to get a percent frequency. Like when we have 0.38 as the relative frequency of Coca-Cola, we just need to buy 100 of this 0.38 equals to 38%. And then now we can write other two lines in the query to calculate the relative frequency and percent frequency. And then this line, the count asteroid divided by 50. This calculated the relative frequency of each drink type by dividing the frequency count by 50. And these steps assume that the 50 is the total number of the cells you are considering for normalization. For example, if a drink appears 10 times, then the relative frequency would be 10 divided by 50, which is 0.2. And this is similar to the calculation for relative frequency, but the result is multiplied by 100 to convert the value into a percentage. So it multiples the relative frequency by 100 to get a percentage representation. For example, 0.2 will become 20%. So this result is analyzed as percent frequency. And then from soft drink cells, specify the table from which the data is being selected. And group by drink name. So this groups the result by the drink name column, means that the count asteroid, relative frequency, and percent frequency are calculated for each unique drink name in the table. Now we can try to execute this query to see what the result looks like. So this is the result for frequency, relative frequency, and percent frequency. However, you can see from result that there are multiple decimals in the result, which I don't like it. It doesn't look good. So what I want is I want only keep 2 decimal in the result so that it looks good for me. And it will be more viewer friendly for the people who actually see the report. So what we can do is we can add a round in the query. The round 2, so this is the function, the round function in the MySQL. It rounds the relative frequency value to 2 decimal place. So I add a round before the count asteroid divided by 50, comma 2. Right, so this is how round works. And then I also add the round, the same thing in percent frequency. So make sure that you round it before multiply by 100. Okay, so because we want to round it at first and then multiply by 100. And then let's execute this query again, and then you will see that the result right now has only 2 decimal, and that is what I want. And at last, you can try the order by. But I didn't wrote it here, but it's not required, it's optional. But if you want, you can try. So this orders the result alphabetically by drink name.
Okay, now let's talk about frequency distributions for quantitative data. Unlike categorical data, here we need to be more careful because we're working with numbers. we created what's called non-overlapping bins. So the non-overlapping bins in the context of frequency distribution for quantitative data refer to distinct intervals or range of values that do not overlap. So each data point will fall into exactly one bin, showing that the bins are multiply exclusive and collectively exhaustive. So there are the three characteristics of the bin design. The module exclusivity means each number can belong to only one bin. For example, if one bin is from 10 to 90, then the next one starts at 20. And no confusion about where 20 goes. And then the second characteristic is complete coverage, which means all data points must fit into one of the bins and nothing should be left out. And the last one is a flexible interval. So usually we keep bins the same width, like 10 to 10, like 0 to 10, 10 to 20, 20 to 30. So though in some cases the bins can vary depending on the data, but like most of the time we want the same width of the bins. So once bins are designed, we can calculate the frequency distribution just like what we did for categorical data, but with intervals instead of the category. So how do we actually build those bins? There are three steps. The first one is to determine the number of the overlapping bins. And the second one is to determine the width of each bin. And the third one is to determine the bin limits. So let's use the dataset of the year-end audit times as the example. First step, decide the number of the bins. So bins are formed by specifying the range used to group the data. So as a general guidelines, we recommended using from 5 to 20 bins totally of any specific dataset. And the most common method to determine the number of the bins are Stir's rule or square root rule. So for example, we can use the log base 2 of n plus 1. So n is the number of the dataset. So if we have data points, for example, in our dataset, the Stir's method gives us 6 bins, but the square root gives us 5. And we normally use the square root. So let's see, we have 5 bins in this dataset. And after we know how many bins, we can decide the width of the bins. So width is the range of the bin, like how many numbers will be included in this bin and what would be the least or largest number of this bin. So as a general guideline, we recommend that the width to be a same for each bin. So we can calculate the width by using the range divided by number of the bins. See, our dataset goes from 12 to 33, so that's a range of 21. And then with 5 bins, width is about 4.2. And then we can round it up nicely to 5. So that means we have the width of the bins as 5. And the last step is to set the bin limits. So once we have the set of the numbers of the bins and the bin width, the remaining decision is to set the value at which the first bin begins. We must ensure that the set of the bins spans the range of the dataset so that each observations belong to exactly one bin. For example, the range of the dataset we have is from 12 to 33, and so the range is 21, right? But the bins range we calculated is the bin width 5 by number of the bins 5, which is 25. It's from 10 to 35. It is more than real range because remember we rolled up the bin width from 4.2 to 5, right? So this means the bin range we calculated is more than the real range of the dataset, so that all of the observations in the dataset will belong to one bin. That makes sense? So in this case, we can start our bins limit at 10 instead of 12, and the end of the bin range would be 35 instead of 33. So Since our bin width is 5, so we can have our bins are 10 to 14, 15 to 19, 20 to 24, and 13 to 34. So this way, each value has a home, and the bin doesn't overlap, and the frequency distribution will be clear and useful. Well, so in this way, every value has a home, and the bins will be never overlapped. And then we can use the bins we created to generate the frequency distribution table with organized set of data into the category or the classes and show how often each category occurs. So here in this table, you can see that the audit time column shows the different bins or classes. So for the time it took to complete an audit, mirrored in days. For example, the first class is for the audit that took a bit between 10 to 14 days. And there are 4 audits were complete in the 10 to 14 days. And thus, the 4 is the frequency. And then we can use the frequency and total number of the audit to calculate the relevant frequency and percent frequency, which is similar how we done in the categorical dataset. So in summary, what we can tell from this table is that the most common audit time is 15 to 19 days, which occur for 40% of all audits in this sample. And the data shows that the majority of the audits were completed within 29 days, with very few taking longer than that. So now let's see how we can complete the distribution for quantitative data in SQL.
So in this case, we were using the table called audit records. Same as before, we were using select asterisk from audit record to check all the data. So now we can see we have 4 columns, and but in this case, the only column we need is audit times. So we're gonna select only audit times from the audit record. There's a mistake, I missed one S, so it's fine. And now we can see that this is the audit times column, and since this is quantitative data, so we will create the bins based on this audit times. And in this case, if we want to use quantitative data to create the bins, we will using case statement to create another column called column time bins. So the case statement goes through conditions and return value when the first condition is met. It's similar to if-else statement. So once the condition is true, it will stop reading and return the result. If no conditions are true, it returns the value in the else class. And if there's no else part and no conditions are true, it returns none. So in the reading material, I provide you link for W3 School website, and you can check the detail. And when we come back to this example, when we're using the case, we can use case to create the categories or bins based on the value of audit times. So the first condition is when audit times is less than 15. So when we write the audit times less than 15, and we use then to provide the value under this condition. So that means when audit times is less than 15, we will give this new column a value called less than 15. And don't forget to use the single quote, because we provided the values for these specific columns. We will use the single quote. And then the next condition would be when audit times between 15 and 19. And in this case, we will give it a value called 15 to 90. And we still use then to make sure that when the condition is fulfilled, we will give this value to the new column. So then we will use the same method to provide other values for other conditions. Like can copy paste here and then just change the value to give 20 to 24 when all the time is between 20 and 24. And same thing when all the time is between 25 and 29, then we'll give it a value called 25 and 29. And then we just have one conditions left, and in this case we don't need to copy paste everything. We can just say else, right? So because like else is when no conditions are true. When no condition above the true, it will return the else clause, right? So when the else, we give it the value as more than 30. When we finish the all conditions, don't forget to insert and to end the whole case. And we will select the audit timeset first to make sure that this is the resource of our bins. And so we can run this query and let's check the result. And now you can see the result. There are two columns. The audit time columns is from the original table. Other columns, the result we get from the case statement, right? However, in this case, we know that the column name means case blah blah blah. So this is very hard to understand. So what we can do is we can create the column names for this new column using the SQL alias method. Remember, we're using s, right? So, and in this case, we don't need audit times anymore, so we can delete the audit times. At the end of the case, add as bins. And after that, we can, using the same method from above, to calculate the frequency, relative frequency, and percent frequency. And in this case, don't forget, we have to change the account of the data set from the 50 to 20, because the 50 was the number of the data set for soft drink sales. But in all the records, we only have 20. So we will change this number to 20. And then we can run this. Oops, there's a mistake because we missed the group by statement. So we have to add the group by. And in this case, we can use the names we used before, right? We can use the name we created as the alias name of the case statement, which is the bins. So, and then the result showing that we have the bins, which is all the group of all the times. And then we have the frequency, relative frequency, and percent frequency. So this is how we created a frequency distribution for quantitative data by using the case statement. Now we're going to talk about the measures of location. In categorical data, the only common measure is mode, which is the central location defined as the value that occurs with greatest frequency. Since categorical data are non-numeric, measures like mean or median are not meaningful. Instead, we rely on frequency distribution to identify the mode. A frequency distribution table lists each category along with the number of times it appears, which is the frequency. So to determine the mode, we need to construct a frequency distribution of the categorical variable, and then compare the frequencies of all categories. The category with the highest frequency is the mode. So for example, in frequency distribution of soft drink sales, we see that Coca-Cola has the highest frequency, which is 19. Therefore, The mode of this categorical dataset is Coca-Cola. In quantitative data, the common mirrors include mean, median, and mode. Mean, also called arithmetic mean, is a measure of center location computed by summing the data values and dividing by the number of observations. For example, here is the home selling price data of 12 home sales. To calculate the mean price, we can do x bar equals the sum of all the values in the dataset divided by n, which is the number of the observations in the dataset. So we have applied this formula to these 12 values of selling price. The final result is 219,000 as the mean. Median is the value in the middle when the data are arranged in ascending order. For an odd number of observations, the median is the mid value. For an even number of observations, the median is the average of the two middle values. For example, consider the class size data for a sample of 5 college classes, including 46, 54, 42, 46, and 32. First, we have to arrange the data in ascending order, which is 32, 42, 64, 64, 56. Here, the middlemost value is 46, so the median is 46. Let's see another example when the number of observations is even. Consider the data on home sales in Cincinnati, Ohio suburb. Arrange the data in ascending order, and then we can see that 199,500 and 208,000 are two middle values. So the median is the mean of these two values, which is 203,750. And as described before, the mode is the value that occurs most frequently in a dataset. So in this class size case, 46 appears more than once and more frequently than any other value, making it the mode. And sometimes when data contains at least two modes, we call them the multimodal data. For example, if we have a class size data as 32, 42, 46, 46, and 42, then in this case, both 42 and 46 are modes. We can call it multimodal data, or we can also call it bimodal data because the data contains exactly two modes. The last part is called variability, which is only applied on quantitative data. It refers to the degree to which the data points in a dataset differ from each other and from the central tendency, for example, the mean or median. It is very important that it measures how spread out or clustered the data values are, providing insight into the distribution and consistency of the data. For example, Fund A and Fund B for $1,000 investments over the past 20 years is shown here. Fund A has paid out exactly $1,000 and $1,100 each year for an initial $1,000 investment. Fund B has had many different payouts, but the mean payout over the previous 20 years is also $1,100. But would you consider the payout of Fund A and Fund B to be equivalent? Clearly, the answer is no. The difference between the two funds is due to variability. There are multiple mirrors can be used to represent the variability. The range can be found by subtracting the smallest value from the largest value in a dataset. Consider the data on home sales in Cincinnati, Ohio suburb. Since the largest home sales price is $456,200 and the smallest home sales price is $108,000, the range is using the largest home sales price minus the smallest home price sales, which is $348,250. However, there is a drawback that the range is based on only two of the observations, and that is highly influenced by extreme values. To figure out this drawback, we can use another measurement called variance. The variance is a measure of variability that utilizes all the data. It is based on the deviation from the mean, which is the difference between the value of each observation and the mean. The deviations about the mean are squared while computing the variance. So, the variance equals to sum of the square of each deviation divided by number of dataset minus 1. So n minus 1 is called degree of freedom. It is a fundamental concept that relates to the number of independent values that can be varied in an analysis. It is often described as the number of the values in a final calculation that are free to change. The 1 is abstract because 1 degree of freedom is lost when you use the sample mean to calculate the variance. The sample mean itself is a parameter that is estimated from the data, which constrain the value. The degree of freedom is not a required concept or content here. It is just a description for you. Okay, now let's come back to the variance. Let's talk about this illustration. We can calculate the variance of the data on a class size of 5 college classes, including 46, 54, 42, 46, and 32. The variance would be sum of the square of the deviation by using the deviation between each value and the mean. So the sum of the square of the deviation is 256, and we divide it by n minus 1. The n is 5 because there are totally 5 observations in this dataset. So the degree of freedom would be the 4, and it leads to 46 as the variance. However, the 46 is quite large to represent the variability as it is a squared value. So we can use another measure, which is called standard deviation. It is a square root of variance and measures the average distance of the data points from the mean. It is expressed in the same unit as the data, making it more interpretable than a variance. And the very related measure is the coefficient of variation, which is a related measure of dispersion, expressed as a percentage, that shows the extent of variability to the mean. It allows comparison between datasets with different units or scales. For example, we can calculate the S, which is the standard deviation, and the CV, which is coefficient of variation of the data on a class size of 5 college classes. So in this case, the mean value is 44, the standard deviation would be 8 because the variance is 64. So the root of the variance would be 8. And then you can calculate the coefficient of the variation by using 8 divided by 44, then multiple by 100%, which is 18.2%. So calculating the standard deviation and the coefficient of the variation help us understand the variability or consistency in a dataset. The standard deviation tells us whether data points are tightly clustered or widely spread. So for example, let's check this funding comparison again. So we can calculate that fund A has 0 standard deviation and 0 coefficient of variation. But fund B has around 587 standard deviation and 0.534 coefficient of variation. So that means fund A has no variability at all. The value is all the same every year. It is perfectly stable and risk-free in this dataset. And fund B has the same mean value as fund A, but its returns vary widely across the years. The high standard deviation shows large fluctuations. And the coefficient of variation measures related risk per unit of the return. So for fund B, since the CV is about 53.4%, that means the variation is more than half of its mean return. And this indicated high risk related to its expected return. So we can have a conclusion that fund A is very stable, risk-free, and it is predictable. However, the fund B is even same average return, but much riskier and inconsistent. So now let's see how to calculate this measurement in SQL and Excel. The best way to explore the measures of location and the variability of quantitative data is to use the descriptive statistic tools in Excel. So let's using the audit record as an example. We can find out the mean, range, median, standard deviation, and the variability of audit times. However, we don't have the data yet. So we have to go to the MySQL to collect the data from audit records. And so this is the whole table of the audit records. But since we only need audit times, so we use select audit times from the audit record. And we will copy paste this table, this data into the Excel. So what you're gonna do is you will highlight this audit times and right click any area of the highlight data and select copy row unquoted. And then we open the Excel and paste the data into the Excel. So now you will find the data on the toolpack and click the data analysis. So this is the tool that you need to allow from the Excel. So in the Mac, for example, in the Excel of the Mac, you can click the analysis tools and then select both analysis toolpack and solver add-in and click OK. The solver, we will use that later. For the students who use Windows, you can click this link I provided in the reading material and follow the steps and to activate the data analysis toolpack if it is not visible. Okay, and then after you activate this analysis toolpack, you can click this data analysis toolpack and then find descriptive statistic and then click OK. And then you will see this statistic window for you to set the parameters. So the first of all, you have to select the input range. So in this case, we have input range from A1 to A20, right? And then we said group by the columns. And then output options, we select output range to C1 because we want to put it here. So if you select the output range, that means you specify a cell or range where the result will be placed within the same worksheet. And since we choose C1, so which means the result will show at column C. And you can also select new worksheet, which is to create a new sheet in the same workbook, which is same Excel, to display the results. Or you can create a completely new workbook, the new Excel, to store the result. And then the third requirement would be the summary statistic. You have to select the summary statistic checkbox so that the tool will calculate the variety of the summary statistic for the data, such as the mean, median, standard deviation, etc. And so that we can see the results shown here. And these results show all the information, including the mean, the median, mode, standard deviation, as well as the range, minimum, and maximum.